Hi then folks, this is a follow-up video to the lesson that I taught in school in the penultimate week of term, just for those that weren't able to come in, or indeed those of you that did can just have a bit of a recap. So in my last trig video we were looking at the reciprocal trig functions, them being that sec x is defined as 1 over cos x, that cosec x is 1 over sine x, and cot x is 1 over tan x. But as tan x can be written as sine x over cos x, the reciprocal of that means that cot x is also cos x over sine x. And that can be quite important for us to use. So these are new reciprocal trig functions. And in the previous video, I asked you to then follow up with this exercise where you do have the solutions. So I printed this out for those of you that were in school, but I think you were able to print it out yourself. Here we've got 1 over sine cubed, so that would be cosec cubed. Here I've got the square root of 2, sorry, the square root of 4 is going to be 2. Then it's 4 over tan, so that's going to be cot to the 6x. If I'm going to square root that, then it would be cot cubed. So this would become 2 cot cubed x. We were using the definitions of sec, cosec and so on to simplify these. I would perhaps tend to often just write these in terms of sine and cos. Cot here is cos theta over sine theta. By the time you times it with that sine theta, then that actually just simplifies to be cos theta. So in question 4 you had some identities to prove, and I showed most of you how to do this first one. Again, write the tan as sine over cos. You then end up with a fraction, and you want to think about adding fractions. So hopefully that's going well, but do email me. Over the summer I will check my emails at least weekly, and if you want me to say, if you say me, oh, how do I do question 4b, I've just got completely stuck, then do let me know. But in class we also then looked at the Pythagorean identities, and earlier on in year 12 we learnt that sine squared x plus cos squared x is equal to 1. A rule that you should know and hopefully be using a fair bit now. And what I did in class is, if I chose to, I could divide all of these terms by the same thing. It will keep the equation balanced. So if I divide everything by cos squared x, sine squared x divided by cos squared x will be tan squared x. Cos squared x divided by cos squared x will be 1. And then 1 divided by cos squared x will be sec squared x. So by dividing all of those things by cos squared, I get a new Pythagorean trig identity. Equally, I could divide everything by sine squared. So going back to the first one here, if I divide that by sine squared, I get sine squared over sine squared x. Cos squared x over sine squared x will then be cot squared x. And then 1 over sine squared x will be cosec squared x. And these are then 3 Pythagorean trig identities that we need to use. So box them off. These are things you definitely need to write down, keep in a safe place. And we're just looking at how to use them. So in the lesson there were 2 questions that I looked at. So this is just a recap of those. First of all, we had a trig equation to solve. And as a trig equation, we're going to solve between 0 and 360 degrees. So solving an equation, I can use degrees. I could have given you the question in radians if I wanted to, but when you're solving, it can be degrees or radians. It's just differentiation and integration where you must use radians. So looking at this, what do we not like about it? It's got the new trig functions in it, so that's new and unusual. We've got a square term, this term isn't. But also, going back to questions we've looked at already this year, we've got different types of trig and we don't want that. But with a power of 2, could this be, is it a quadratic? And that's where you want your mind to start kind of going and thinking, well, how would I deal with a quadratic? Now we've got cosec and cot together, so is there an identity that links them? And there is here. So actually the cosec squared could be written as 1 plus cot squared. And that's got the same type of trig, so that seems like a sensible place to start. So we'll replace the cosec squared with 1 plus cot squared. Doesn't look overly pretty, but if it is a quadratic, well, we've got a cot squared term and a cot term, then all quadratics, they always equal 0. So let's multiply out this bracket, tidy things up and get it all onto one side. So we've got the 4 cot squared theta. I'm going to bring that individual cot theta over, and 4 times 1, take away 9 will give me minus 5. Now I've got a quadratic here. If you wanted to, if it felt nicer, you could write it using a different letter perhaps. That might help you to see. Obviously if it factorises, that'd be amazing, because factorising could be quite quick, or I could use the quadratic formula to do it. So pause the video, spend a bit of time thinking about just solving this quadratic, but I will show you now that it did factorise. It wasn't obvious that it splits up to 4 cot theta and cot theta, because it could have been 2 cot and 2 cot in the brackets. But then we want multiples of 5, and if I put them in this way round, let's just double check. That's going to give me minus 5 lots of cot theta. That will give me plus 4 lots of cot theta, so that give me the minus 1 in the middle. So that means then that cot theta is equal to 5 over 4, or cot theta is equal to minus 1. Now my calculator, might have a shiny white calculator, but it doesn't have a cot or cosec or anything on it. It's only got the sine, cos and tan buttons. So let's not solve a cot equation. Cos is the reciprocal of tan. So if we make it into a tan question, we just want to find the reciprocal of that, and that means that instead of solving cot theta is 5/4, you want to solve tan theta is 4/5. Need to do the same here on this one. Of course we've got the reciprocal of 1, which is going to be 1, and of course it was a negative 1, so I've got to keep it as negative 1 over 1, so probably better to just leave it as minus 1. Then you're going to do your inverse tan of 4/5, and get your value for that. Now I was in radians just now, so I'll go back into degrees. Inverse tan of 4/5, 38.7 degrees. And it's a tan question, so I want to think about the pattern of getting more results. And tan's the nice one, you just keep adding 180s. So I'll add 180 to that, and I'll get another answer. So theta is going to be 38.7 and 218.7 degrees. Obviously if I add another 180 to it, I go beyond the 360 that I wanted. But I do have that second equation to solve. So inverse tan of minus 1, we might know what that is. It's minus 45 degrees. Now of course that's not a value that I want, but if I add 180 to it, it will give me a value that I want, so 135. And if I add another 180, I'm still within the range of values that I wanted. So I've got my 4 solutions to this particular question. Take a step back and think about this. Nothing massively new actually. You have solved quadratics in disguise and used that identity before to manipulate them, but we turned it into a quadratic. It did factorise, but you could use your calculator to maybe get these 5/4 and minus 1, but you just need to then show a method. So I perhaps use my calculator and then go back and put the factorise, just to get mini equations to solve, and then you're just thinking about how to solve mini equations. So that's solving an equation. We're then going to have a look at proving an identity, and in the handout that I gave you in class, and if you haven't got it, then you could just pause the video and look at it. We're looking really at how to simplify some of these questions, and on the next page we're looking at proving some identities. Now I've given you worked solutions as well, so I will let you have a look at that in your own time, and again email me any requests for questions. But the one that I did in class was this. We want to prove that cosec to the 4 theta minus cot to the 4 theta is identical to 1 plus cos squared theta over 1 minus cos squared theta. So we've got an identity. It's not an equation where I want to try and move things from left to right and find theta. What I want to do is, can I show that the left-hand side can be written as the right-hand side? So we want to start thinking about what we like and what we don't like. Neither side looks particularly great. I could try and manipulate the right-hand side and turn it into the left, but generally 9 times out of 10 we're going to start on the left and go to the right. Now, of course, here we've got our new trig, our reciprocal functions, which we haven't used in the past. And also we have powers of 4 and there's only powers of 2. So I want to think about how to deal with this, and the sneaky thing here is it does factorise. And I'm just going to give you some examples of questions that factorise. If I ask you to factorise x squared minus 9, you're going to get x plus 3 and x minus 3. The difference of two squares. Two squared numbers two squared numbers and take away the difference. I could give you 16x squared minus 9, and I've specifically given you 16 because it's a squared number, and that'd be 4x plus 3 and 4x minus 3. And just think about multiplying that out as to why that might work. But I could give you y to the power 4 take away 81. And this is again two squared numbers. 81 we definitely know is a squared number, and power 4 is a squared number. In fact, it's a squared number squared. So this factorises to be y squared plus 9 and y squared minus 9. Now it does happen that the 9s are also squared numbers, so that could have factorised to be y squared plus 3 squared and y squared minus 3 squared, because the question actually could have been factorise y to the power 4 minus 3 to the power of 4. And then after doing that, hopefully you can see that this factorises. So factorising is something that we always want to try and do. And of course by doing it, we've suddenly now got powers of 2, which is much better. Just takes a little while to write out the brackets. Now we want to just think about, well, how is this useful? And we are going to think about just our Pythagorean identities. They've got the squared in them. So I want to be thinking about those 3 rules from the start of the video, and is there one that links the cosec and cot together? So save me turning over the page, but you would have had on the previous page, you should have written down in front of you that 1 cot squared x is equal to cosec squared x. I could use theta and theta. So let's have a little think about it. If I rearrange this, does this identity appear anywhere here? Well, they're on different sides, so I need to obviously group them together. So I'm going to have to bring that cot squared x over to the other side. And if I do, then I'm going to get 1 is equal to cosec squared x minus cot squared x. Cosec squared x minus cot squared x, that's what we've got here. This bracket actually is equal to 1, which massively simplifies what we've got, because when we times that bracket with this bracket, then actually this first bracket has been times by 1, so I've just got this bracket on its own. So I've got squared terms, which is where I was wanting to get to, but of course this doesn't look anything like what I want to do. But now that the factorising has helped me deal with the powers, I will now start to write these as fractions. Always a good idea to write your reciprocal trig functions, write everything in terms of sine and cos. So we've got 1 plus sine squared theta, and cot is cos squared theta over sine squared theta. So we've now turned it into fractions that we're adding together, and actually I'm pretty happy here because our fractions have both got common denominators already, so I can just add them together straight away. Occasionally you'll find that you might need to get common denominators to sort it out for you. So I should really put an equals every time each line of work as I move down the page. Now look at this compared to the keeping our eye on the prize. Pretty happy here. Got a fraction, and the top of the fraction is exactly what I want. Of course, looking on the bottom, sine squared theta, how can I manipulate that? Well, if I use sine squared theta plus cos squared theta is equal to 1, always a good idea to perhaps just jot it down to the side. Then sine squared is 1 minus cos squared. So I then have got the final result that I was after. Sometimes you can put a little square to say finish, you can write QED, I can't remember what that stands for in Latin, but I've done it. This is the right hand side. I started with the left hand side. In this case I did some factorising and had a bracket equal to 1. I then wrote them as reciprocal functions, as fractions, added my fractions and used another identity to get me the value. There's going to be another video to follow up from this, which will help you now to look at questions like number 2 on this exercise. But before you do that, have a look at question number 1 and question number 6. You then probably can also do question number 8. I wonder how many of these are quadratics in disguise. Okay, thank you for now.